So our afternoon speaker is Dr. Gert Cauwenberghs. He is a professor of bioengineering and the co-director of the Institute for Neurocomputation at UC San Diego. He received his PhD degree in electrical engineering from the California Institute of Technology in 1994 and was previously professor of electrical and computer engineering at Johns Hopkins University and a visiting professor of brain and cognitive science at MIT. His research focuses on micropower, biomedical instrumentation, neuron silicon and brain-machine interfaces, neuromorphic engineering, and adaptive intelligent systems. He received the NSF Career Award in 1997 and the Presidential Early Career Award for Scientists and Engineers in 2000. He's a fellow of the IEEE and the American Institute for Medical and Biological Engineering. I'm very pleased to welcome Gert to be our keynote speaker for this afternoon.
Thank you very much, Katie, and so welcome everyone. Great to see you here virtually in this, we all live now in this Zoom world. So please feel free to interrupt at any time, as if you have a, if you disagree or you have a question, something unclear, please shout out. Feel free to unmute yourself and shout out. I won't be able to see your the chats or your blue hand that you raise in the Zoom window, but so please just feel free to speak up during the talk. So I will make this partly a discussion of where we stand in the field now, but also give a little bit of a historical perspective, since neuromorphic engineering has been around now for many years. In fact, about 30 years now, starting with Carver and Mead at Caltech, who coined the term neuromorphic engineering at that time. And so it's been really an adventure over many years, perhaps in stealth mode for many years, and now really has come to the forefront. So it's important to have a bit of a perspective of where things have come from, and so what have been the challenges all the way along the way. So it's good for us to, as a community, to see where we are and where we're going. Now, just a few years ago, we had almost a revolution in artificial intelligence. At least that's how it was portrayed, as basically the machine who won over the human, right? In a this was an AlphaGo, Google DeepMind's AlphaGo, defeating Sedol, the Go world champion, in this game of Go. And this was very significant for AI because for 30 or 40 years, in fact, almost 50 years, in a way, this computer Go has been the holy grail or the grand challenge in AI. And it was thought even just 5 or 6 years ago, it was even perceived that this would be still a very difficult task to solve with all the supercomputing power that we have available in the world. And so yet it happened. But interestingly, if you go under the hood of how it happened, there's actually a substantial amount of neuroscience happening there, right? In fact, the founders of DeepMind in London were actually neuroscientists, and so they were actually recording from monkeys and cortex, and so they had the models of learning here implemented in this system were actually inspired by the brain. So you had deep learning inspired by the cortical representations in the brain. And then you had reinforcement learning, basically you had models of reward-based conditioning modeled by some of the dopamine pathways that you have in basal ganglia. And so there's very much of an infusion of neuroscience that really made AI happen. And I would actually argue that in some way, it's really the neural networks that really, the neuroscience that pervaded over some of the symbolic reasoning that has been so long the hallmark of artificial intelligence. So today's AI is very different from 50 years ago. And it really made a big difference. And that's, I think the convergence of neuroscience into AI is what really has made it happen, has made the revolution in natural intelligence happen. Now, there's also an unfairness in all this. If you generally give Sedol about 100 watts of power, metabolic power, basically how he was basically moving his body also while trying to defeat the machine here. But then you have 100 kilowatts of power of all the machinery. In fact, the deep pockets of Google in this with this massive servers, GPU clusters, and actually also TPU special purpose engines behind, so far in the deep cloud here. So the important point here is that, sure, AI defeated humans, but there's much more to be learned here. And so that brings up an earlier point raised by Cauwenberghs and others, right, that started this field of neuromorphic engineering. And it's not just about getting at the performance of machine learning in terms of what it does, but also the representation of how it is done and what are the physical primitives, the physical primitives that are used to implement the machinery that can make it happen. And so taking inspiration by biology will allow us then not to only have systems that perform well and hopefully get on par with human intelligence, but also that are equally efficient and resilient in their computing, owing to adhering to some of the same fundamental physical principles of how computation is organized, right? And that's really a very important premise that has been a bit overlooked also in recent advances in deep learning and artificial intelligence. Let me go back to many years. So Richard Feynman, he's very well known for many advances in physics, quantum physics. He also started, in a way, the revolution in information technology, if you want, by pointing us to there's plenty of room at the bottom, right? So nanoscale engineering will allow us to do great feats of information. Well, you didn't really think about information technology, but you definitely thought about the fundamental physics of really going to the nanoscale for doing computation. Cauwenberghs also has started a first revolution in VLSI systems, where he took a systems approach to circuits and systems, integrated circuit design, that led that by taking level abstraction in a design allowed to tackle very hard, difficult problems so we're then with millions or billions of transistors, you can really get at the at performance at a different level of abstractions rather than to keep adhering to the level of single devices that has been more prevalent before the advent of this the VLSI revolution. But those two are also, in a way, started this revolution in neuromorphic computing. Richard Feynman told us, in fact, this was a note that he wrote on the blackboard, just in fact a day before he died. So one of the quotes here is, "What I cannot curate, I do not understand." Right. So that points to, if you want to really build, if you want to understand something, you need to be able to actually build and reconstruct it from first principles. Right. And that's really the foundation of neuromorphic engineering, which then Cauwenberghs has taken to heart and pushed forward with analog VLSI and neural systems. Right. In fact, Richard Feynman, Cauwenberghs, John Hopfield started at Caltech this investigations of physics of computation, basically taking inspiration from biology and physics, right, to really come up with principles of computation that are very different from the usual digital abstraction that we have still prevailing in today's computer architecture. And it's important to consider here the multi-scale representations that we have here in the brain and then in machines in silicon emulating that intelligence. So we have this multiple scale representations all the way from ion channels, with you have ions moving through ion channels, all the way to whole brain dynamics, right? And at all these levels of representation, you have an isomorphism of physics that also takes place in silicon. And so there has been the major realization in neuromorphic engineering that you can take advantage of those isomorphisms of, say, how ions move through ion channels, right, versus how electrons or holes move through channels of transistors using some similar Boltzmann physics, and you have similar then principles of Boltzmann physics also playing out at a network level, where you can take advantage of these different representations then to build systems that scale all the way up, right? So it's important to also emphasize here the dichotomy, the dualism between engineering and science. Science is about analysis, reducing complexity to simple problems, whereas engineering is about synthesis, putting things back together. So neuromorphic engineering, in a way, complements the traditional neuroscience approach with a systems approach that allows to really put together from bits and pieces in a hierarchical fashion how the brain works. Right? So going back from the individual level of devices or elements of molecules, all the way down to whole brain system level systems. And so there have been some beautiful isomorphism in physics, and then I can go in detail here. So basically, for instance, you have this orders of magnitude of dynamic range that you have in conductance versus voltage, owing to the Boltzmann physics of how ions with ion channels, and also how those channels would change based this protein folding entities would basically change based on voltage across the membrane. And so you would have those exponential dependence, right, to the Boltzmann distribution of conductance or current versus voltage that also plays out with transistors in the subthreshold regime of operation, where you get currents that vary over orders of magnitude from femtoamps of current to nanoamps of current, so 6 or more, 6 orders of magnitude of dynamic range in voltage, right? And this tremendous gain that you have, then this range, and also the tremendous gain in this voltage range, also allows you to build very efficient circuits. And this is a mode of operation that typically has been ignored in circuit design. That region of operation, the subthreshold regime of operation, has typically been relegated to the noise and leakage regime. But you can actually take real advantage of that regime of operation for doing physical computation that take advantage of the same Boltzmann distributions, building ion channels that have some of the same dependencies here. So basically build silicon ion channels and conductances. And so that started this revolution, this initial revolution in neuromorphic circuit design, where the community, in this case, Kolabena Boanen, at the time at the University of Pennsylvania, then at Stanford University, developing different generations of silicon retinas, right, where you have transistors innately implementing some of those circuits in this innerplex and outerplex layers in the retina, for implementing, in this case, different types of horizontal cells, bipolar cells, and then also on and off sustained and transient ganglion cells, all with basically physical primitives. And the green dots here are then phototransistors that model then the further transduction that you have. And it's actually quite amazing that from a very rough model of retinal function, that you can actually retrieve information. So purely from looking at transient responses of cells, on and off responses, they can actually reconstruct and what's happening in the visual scene. And it's actually amazing indeed how our visual system can really look at the world from just this optic nerve that only has a few 100,000 fiber bundles spiking at each about 100 hertz or so. We can actually still get the entire complexity of what we see through this amazing visual system that we have, with amazing compression of spike-based coding. Here's another example. So this is, rather than this on and off spatial processing, this is then temporal processing, temporal differencing, right, where by just adding a few more transistors in each pixel of an active pixel sensor, you now attain then great compression in temporal coding in the image. So basically just coding temporal changes in intensity. And so this paradigm has been taken to a very significant level in the community. So now we have what is called dynamic vision sensors that can do an alternative to traditional frame-based sensing. So rather than continually sending frames of images, what you send now are events, or change events, right? So for each pixel registered as address events that are communicated then to the system. And so if nothing changes in the scene, nothing is transmitted. So the data rate of transmission is directly proportional to information that we have as it happens in the scene. If nothing happens, nothing is transmitted. And so then you get a more efficient coding directly on the focal plane of what is happening here at very low power. So now actually we have systems that operate at just a few hundreds of microwatts of power for the entire system at megapixels resolution. So this brings up an important point. So you have had this community of neuromorphic engineering basically build sensors that are event-driven. And then the challenge has been to take that event-driven spike-based representations, and then just the same way as in the brain, you have cortical representations that are spike-based, that now you can do this information processing in an event-driven fashion. And there's several advantages of this event-driven representation that allows you for doing the reconfigurable computing that has really been driving this field of neuromorphic computing in a flexible, multi-chip, modular fashion towards building larger scale systems. This event-based representation, in which spikes are abstracted as addresses of where events happened. So each neuron is given a unique address, right? So this event-based representation allows efficient transmission of those neural events from one chip to another chip to this, right? So with a shared data bus, we take advantage of the high bandwidth of digital communication that you have then through this asynchronous representations. So events that are then coded with address and also implicitly with the time at which the events occur, right? And this has been extended then to not just doing one-to-one mapping from source to destination, but also allow and implement reconfigurable synaptic connectivity, in which then tables so lookup tables will then define connectivity for each presynaptic address, for each presynaptic event, and now you have a list of post-synaptic destinations, along then with the synaptic strength and probability of release, etc. So different parameters of synapses that will be coded in tables, and all this is then reconfigurable, basically by changing elements in the memory. You can then change them basically your connectivity basically on the fly. And so this allows them to implement biologically inspired learning rules, such as spike timing dependent plasticity, which we have extensively talked about. It's important to note that in addition to this biological inspiration of this temporal asymmetry that we have in the change in effectiveness of a synapse based on the relative timing of pre and post synaptic activity, this kernel of STP, in addition to doing the traditional view of Hebbian learning or unsupervised learning, it can also be extended to much more complex models of learning that include deep learning. If you think of this STP, this spike timing dependent plasticity kernel, as an eligibility trace, eligibility of a synapse for change based on where it stands in the network by looking at gradients of information as it flows through the network. The point here for neuromorphic computing is that this kernel, this STP kernel, can be directly and efficiently implemented by using then this event-based representation, because you have the spikes available to you at your tables, and you can just update the tables as you go with this occurrence of pre and post synaptic times, events as they occur. So important note I want to make on complexity is that if you want to go from our simple systems, number of systems that have been demonstrated to date, to really complex systems, we get some major advantages owing to the innateness of the innate analog reasoning aspects of numerical computing, as opposed to the traditional digital symbolic AI reasoning. And so to give a perspective on this, so why has neuromorphic engineering not taken off over until now, so after 30 or 30 years of endeavor? Well, over the last 30 years, Moore's law has allowed this almost exponential rise in machine complexity in terms of density of integration and the number of transistors you can pack on a chip that allowed, so with each exponential rise in machine complexity, there was an equal exponential rise in task complexity that you could handle. Of course, this trade-off is not a great one because at some point, of course, Moore's law is hitting a brick wall, and there's no further to go here, inching on this log scale of complexity. But that's where now neuromorphic engineering can really take off and extend this reach of what can be accomplished in terms of tasks with limited machine complexity, right? This favorable trade-off that we have for neuromorphic approaches versus then AI-based approaches or rule-based approaches, in which if you want to get an exact answer to your problem, if you want to conduct an exact search, you're paying a price that is at least linear in the complexity of a task in terms of the computation you need to perform, right? Now, in order to really get these advantages of complexity, it's important then the scaling, right? So it's important to do two things here. One is to abstract from the complex world lower complexity representations through deep learning that can bring down then the complexity of representations and your machine complexity. But also it's important to venture in this range of neuromorphic engineering, or in this range here of high complexity, where neuromorphic engineering will really stand out over more traditional approaches, right? So AI, so traditional digital computing is easy for low complexities, but so neuromorphic engineering can only shine really in this domain here, in this gray region, where then this analogical reason with this scaling would actually have an advantage. So it's important to go in this regime, and if you want to get anywhere to the level of intelligence of human brain, it's unlikely that we can do this with less than 10 to the 15 synapses, because otherwise the human brain through evolution would have gotten rid of most of its machinery, this complexity. So it's unlikely that we can do things with less than 10 to the 15 transistors or memory elements. So we need to venture in this domain here. So there are a few. So it's important then not only to think in terms of algorithmic advances, but then also in terms of device level advances. And those two aspects, those complementary aspects of optimization, also nicely decompose if we look at the energy per task, what we're trying to minimize here, right? So the energy per task can be decomposed as energy per operation times operations per task. And we can make great advances in deep learning and representations, so algorithmic representation to minimize operations per task. I'll see more about that later. But with neuromorphic engineering, we can also then really optimize then lower basically your energy per operation. So going from the typical hundreds of picojoules per multiply cumulate that you have now in GPUs, 10 picojoule is a very aggressive estimator for what GPUs are doing today, down to the femtojoules per synaptic operation that you can do then with carefully optimized neuromorphic computing that do processing in memory computing, right? So, and there's several aspects of multidisciplinary endeavors that can really get us there. And I'll just highlight a few here. So then for deep learning optimization, we want to have means for having better representations of the environment, and also means for getting enough data to actually really make advances in the algorithm modeling. But then on devices and systems level, we need to have means for representing the hierarchy, the complex hierarchy of large-scale systems with up to 10 to 50 synapses, with both high density, but then also with scalable connectivity, and really being able to get down to the femtojoules per operation efficiencies that we have with a human brain. So here's a summary of some current state-of-the-art in large-scale reconfigurable neuromorphic computing. So those are systems that go from industry and from academia, right, where you have where you can change the connectivity on the fly, and or train the connectivity in the fly, while also having then a large number of elements available to you. So several thousands or millions of neurons, and billions of up to, I guess, close to 1 billion synapses in the true nerve system here. Now it's important to then think of different metrics, and there'll be another session later at ICONS where we have different benchmarks for neuromorphic computing, and it'll be important to discuss those. One of those benchmarks that is at least easily quantifiable is energy efficiency in terms of joules per synaptic event, right? How much energy do you expend for the synaptic operations that you're doing? And if you do this comparison across the different analog and digital implementations that range here from IBM True North, Louis Intel, and the Spinnaker systems at Manchester, those are digital implementations. And then the analog implementations, the facets of brain scale at Heidelberg, Stanford Neurogrid, and also our IFAT system that we have here. So if you look at across the board, you have energy efficiencies that range down to about upper the 10 to 20 picojoule per synaptic event. And you can ask yourself, is that the limit? Well, we definitely want, that's still a factor 10,000 away from what the human brain is doing. But at least we're getting much better than some of the current digital implementations. If you go to the supercomputer center, you'll be getting roughly around nanojoules of energy per synaptic operation. So this is progress, but more progress can be made. An important consideration is also is not only scalability in terms of the size of what you accomplish, but also how, I mean, so what is the, so how well can you connect across different scales in your hierarchy? And that's important. So in the brain, we have gray matter, but also white matter. The white matter is your connectivity that ranges across brain regions. So for instance, you have the two hemispheres connected with a bridge of fiber bundles, right? And so you have very sparse connectivity there, but still a very important connectivity that needs to be maintained. And so in terms of a network of scaling to that level of connectivity, it's important to have this efficient representations, more like a tree structure, where basically the number of hops in this network to reach far destinations will be logarithmic in distance rather than linear in distance, right? And that's critical in order to scale to large systems. You want to have a small world topology in your implementation, just the way as you have this small world network that you have in the brain. At the same time, it's also important to have flexible connectivity, right? So you want to have a tree-based structure, but also you want to have some arbitrary connectivity so that you can actually right? So you want to be able for every neuron to connect to every other possible neuron in your system, while this is not a full connectivity, right? So you want to have this hierarchical connectivity with a tree-based efficiency, but also then have arbitrary connectivity at the same time. So you want to have so hierarchical address event routing is a representation is a means for doing that. There's some other ones. Spinnaker also has a similar approach for doing this long-range connectivity as well in efficient manner. And the principle here is fairly simple, that you have this multiple levels of representation in your connectivity, where you can have this lookup tables that define your connectivity that I showed earlier. But now do this add leaf nodes in the hierarchy. And so you can have very efficient local connections, densely implemented at the leaf nodes in hierarchy, but you still have long-range connections by basically going up in the tree, right? And have these relay neurons at each level in representation. They will then pass events from a lower representation to a higher representation and sharing them with the peers at that level. And so this allows them to make implement a small world network in an efficient manner, where all you have to do is basically to represent not only the synaptic information that is done at the leaf nodes in the hierarchy, but then also those routing tables that will then pass information through the hierarchy. And all that's needed in those tables is not synaptic information, it's purely the pointers to local representations of that neuron state at the destination, right? So there's some translation that you have of local information in each table here that can be efficiently implemented in those tables here. And so this all scales nicely as long as your connectivity, your fan out is constant. You can scale up your system twice larger. You have twice greater network. If the fan out is the same, you have the same bandwidth of communication across all the nodes in your network. So we implemented this hierarchical address event representation with a system of what we call IFATs, integrated fire array transceivers, that implement then the analog continuous time dynamics of synapses, synaptic conductance, and then neurons, while then also having then the hierarchical connectivity, synaptic connectivity implemented in these lookup tables, distributed across the architecture to the different nodes, with peer nodes here, with FPGA serving them, peer nodes in the architecture. And so this all scales. You can have multiple racks, different boards and racks of those systems that they can extend this architecture for long-range connectivity. And so here we have about 22 picojoules per event at this IFAT level owing to the efficiency of the analog implementation for the event-based neural transduction here. So how do you go from here? So clearly, so we're limited here. This 22 picojoules is limited basically by the DRAM access that you have, right? You have this analog chips for implementing this neural arrays, and then you have your DRAM on the side and the FPGAs, right? And so you have the DRAM and the FPGAs here implementing this connectivity. So clearly, you can do much better if you can integrate this memory and the lookup tables within along with your neurons. And so several lines of work in implementing emerging memory technologies that are called memistors or resistive memories or phase change memory, ST-RAM, etc. They're all operating in this variable conduction mode, right? In which you have memory elements that can be activated just with a word line, and they can get a conductance that varies over with a certain dynamic range, where the conductance can be changed through adaptation, through basically set or reset operation. And you can accumulate, you can get that information along your bit line. But the same paradigm can also be used directly as a neuromorphic synapse, right? Since your word line can really then code your presynaptic action potential, activates that word line, And then you can accumulate, you can think of the bit line as your dendrite that accumulates then this currents from these synaptic conductances that you have for an entire row of those elements. And so then you can have a analog implementation of a synapse actually innately in for each memory element. Think of this as the extreme case of a processing in a memory system, right? Or a multi-core system where each core is just like one memory element. Right? There's a compute here, this synaptic compute. Phase change memory is one important technology. Duigo presented plenty of work yesterday, and I won't go into too much detail on the device physics, but there has been some great advances then including now Intel has now 3D cross-point optene technology at the giga scale with multiple billions of those elements that can be integrated on a single stack of dies. Duigo also did some great work on implementing STDP, spectrum independent plasticity learning on this crossbar arrays of phase change memory. This was work she did with Philip Wong at Stanford. And this is also the starting point for a calibration that we now have at embedding now those crossbar arrays of synapses with crossbars of neurons, those neural integrated fire array transceivers that I just talked about. And it's then possible to embed or integrate those synaptic arrays along directly interfacing them with this neural arrays at the finer grid below, right? So, you could either do that in the back end of the line, because directly above the CMOS, or you can integrate that along with the CMOS on the side. And so in a recent implementation, so this is layer one, and Raj Kumar Kabandran, who just spoke also in the session before this, in collaboration with Stanford University, Philip Wong's group, and also with Tsinghua University. So we developed this neurosynaptic core that integrates then this RRAM, resistive RAM elements directly with CMOS in a fine grid fashion, right? So where you have this array of neurons that are integrated then with arrays of synapses at finer scale. And there are actually great advantages of doing this interleaving of this CMOS and RRAM integration at this fine scale, because this also allows to transpose the connectivity by basically flipping a switch inside this block where you have this neuron interfacing with a subcore of 16 by 16 synapses, this RRAM synapses. By basically flipping a switch here, you can revert the connectivity of your network by inputs going vertically versus inputs going horizontally in order for then implementing a transpose operation in your network. And that's important because then you can do backpropagation learning. You can revert the direction of your connectivity, but you can also then do this inference and generation, this iterating between inference and generative modeling in this Boltzmann machine or this autoencoders, right? Whereby reverting direction, you can basically have this wake phase, right, and this sleep phase and wake phase alternating of doing generation and inference that are part of this Boltzmann machines for generative modeling. And so we implemented this chip in this was in a 130 nanometer process with integrated. So this is one of the first chips actually where there's a true integration of CMOS with RRAM and actually implementing, in this case, a Boltzmann machine on chip. Right, so there have been plenty of implementations where you have a crossbar array separate then from the CMOS on the side, but here this integrates this now in a fine-grained manner. And also we have advanced the efficiency. So in this case, we get about 13 femtojoules per synaptic operation, owing to this very tight coupling of the compute and the memory operations here, right? So directly with the synaptic operations I have here, the synaptic kernels that they have here. And there's some other advantages that can not go over here, where we do voltage sampling rather than current sampling for efficiency in this multiply cumulates. There are several challenges that you have with RRAM, sneak paths, etc., that we're able to address here quite efficiently in this implementation. So this was work we presented at ISSCC earlier this year, and also we have a follow-up paper at VLSI a few months ago, where we also discussed some further extensions on the architecture for efficient mapping of networks onto this different architectures, different deep learning architectures onto this synaptic fabric here. And so, as I mentioned, so the advantage of this representation of this reconfigurable implementation is that we can do this inference and generation in alternating fashion. So in this case, we can do this reconstruction of basically, if you can present a noisy or a occluded input, we can then reconstruct the input by basically regenerating from the representation, so basically a generative step after the inference, and then basically filling in the missing information. That's a key aspect of this generative modeling you can do with these autoencoders and these reciprocal Boltzmann machines that are typically missed in most feed-forward neural networks that you have, this more traditional deep learning architectures. And so we're able to get similar performance then to a software simulation with much lower power. This shows then the system in operation. This was a demo we presented at ISSC in February, right, where you take your input, your MNIST reduced input, you occlude a few pixels, just change a few pixels intensities, and then you throw it at your network, both in software and the chip, and it shows that you can get the same reconstruction at the chip at much lower energy that you have for your system, the chip, rather than in the software simulation. So in terms of algorithms, so in addition to these Boltzmann machines that we have here in on this RRAM CMOS chip, we also have further extended this Boltzmann machine framework for doing stochastic sampling. And an important aspect of neuromorphic computing is also the ability to take advantage of stochastic representations. The fact that synapses are not deterministic engines, they are very stochastic. In fact, in the brain, in our brains, synapses fail to have their postsynaptic conductance activated at about 50% of the time, or actually more than that, almost 70% of the time, that synapse is not being activated by presynaptic action potential. So there's a lot of stochasticity that is innate in neural and synaptic representations that are not accidents. They're not accidents in biology, but they have good reasons in their presentations. In fact, stochasticity is key to having robust, redundant representations that allow for greater generalization. In fact, drop out and drop connect are actually used in deep learning for getting more robust representations, that generalize better. So noise injection is an important aspect. They can also be harnessed then in neuromorphic computing. And so neuromorphic synapses typically are noisy and stochastic, and we can really take advantage of that. So this shows that, and in fact, we're able to operate the stochastic sampling machines where we have this stochastic synapses at even greater efficiencies. So with fewer operations, we can actually get higher recognition accuracy with fewer operations than this digital Boltzmann machines implemented in software. We are, in addition to the CMOS-RRAM implementations, we're also now building systems in FPGA-based hardware that scale up to large systems. So as part of a National Science Foundation project, we're developing now a community resource infrastructure, for neuromorphic computing that will have 128 million neurons and 32 billion synapses with 32 FPGA boards that have high bandwidth memory coupled then to this network of high bandwidth interconnects. And so this extends on this higher hierarchical address event routing framework with now also this neural synaptic array transceivers where you have tight coupling between memory and compute at each core level in the architecture, implementing also learning kernels, SDP, and other learning kernels that are then neuromorphically based. So this will be available for the community in about a year from now through the Supercomputer Center at the San Diego Supercomputer Center through the Neurosciences Gateway. A few words on efficiency in representations. So you can get down to 13 femtojoules per operation, as I mentioned in this CMOS-RRAM engine. Can you do better? Sure enough, we have actually even gotten to the femtojoule per synaptic operation mark, but in a highly specialized architecture. In this case, if what you're doing is, so rather than doing reconfigurable computing, if you're doing a fixed kernel, in this case, you have a fixed size of a support vector machine, so a fixed number of it, a fixed dimensionality of the input, and a fixed number of support vectors. You can map it very efficiently in hardware. In this case, by coupling, by doing a charge mode multiply cumulative operation using just a few charge coupled devices, along with DRAM storage of your memory elements, we're able, and also then by doing efficient coupling of this charge domain computing with a resonant tank through an external inductor, basically where we then recover the capacitive energy for that is expended by driving the lines. Through coupling that energy with this external tank, we're able to really bring down the power tremendously for this processing and memory computing down to the femtojoule per so teramax per milliwatt is about a femtojoule per synaptic operation, and that's on par with the energy efficiency of the human brain. 10 to the 15 synapses operating about once per second, with firing about once a second at about 15 watts of power. So it's about a femtojoule of a synaptic operation. Of course, the brain does much more than that, but at least so we're able to get at a nominal energy efficiency of the brain with systems that of this charge-based computing. And I should say that if now we go from this 250 nanometer technology that we did in 2000 in the early 2000s to today's 22 nanometer technologies, you can bring this down tremendously. It can go down to from the femtojoules per synaptic operation, you can go down to attojoules now. So we can even go a factor 100 or so higher than the human brain. So that's an overview of neuromorphic computing, where we have been over many years, and also where we're going. I'd like to highlight a few more directions of where neuromorphic engineering can also bring us, and that's the direct physical connection to the brain. In addition to emulating neural systems in silicon, we can also use silicon as a means for efficiently interfacing to the brain, and we can then have neuromorphic neural interfaces that not only will be efficient at communicating with the brain and able to disentangle unravel the complexity of the brain in computational neuroscience or computational systems neuroscience, but also then actually interface intelligently with the systems, with biology, speaking the same language of the brain through of spikes, right? So basically have spike-based systems that can also interface with spikes in biology. At a more abstract level of representation, we can also use then neuromorphic computing as a means for modeling interactions that we have between brain, mind, and body. And here this shows some effort that we had at the National Science Foundation, and where we coupled different modalities of brain and body activity imaging, along then with metrics for then and training the brain and the brain's plasticity to alleviate problems of in this case, Parkinson's disease, basically motor disorders in the brain through this closed loop systems. And then having good models of what the brain is doing is key here. So you can think of also means for neuromorphic computing to couple with intelligent closed loop neuromorphic neural interface systems. And this is not limited then to invasive systems for interfaces, but you can also couple that to non-invasive EEG-based neural interfaces where you can then do real-time localization of activity, brain activity. So basically use then neuromorphic and signal processing and blind source separation for then figuring out what is happening in the brain, basically separate sources of the brain in the brain as it happens in real time for different tasks of human-computer interfaces. And so with that, I think we have, we'd like to close the loop here with neuromorphic computing, extended to this different levels of intelligence here, where we can use these neuromorphic systems for studying the interaction between neural systems with the environment. They can also translate to more intelligent systems of silicon microchips that interact with the environment. And so with that, I'd like to thank because many people that we have collaborated with over the years and that we're actively collaborating with now, and also several funding agencies here. And also I should point out, it's an exciting time. So this virtual format that we have now at ICONS is actually, so in a way, to some extent, we can almost thank COVID-19 for bringing us together. There are all those opportunities now for Zoom-based worldwide interactions that we have. Next week, we have the first virtual Telluride neuromorphic workshop. The workshop has been held since 1995, so we actually celebrate a 25th anniversary this year of the workshop, and has been for 24 years. Has been a physical workshop at Telluride. This year it's virtual, and so over years we had we're limited in attendance, so we had basically about around 100 people that could attend, students and faculty and researchers from both academia and industry that attended this intense hands-on workshop, putting chips and robots in this very idyllic setting of 10,000 feet. This year it's virtual, which means we can't do hands-on, but at least there are now more than 500 attendees. That'll be next week. Converging, and then there'll be some team projects that can continue after that. So things are quite exciting. And with that, I'll just leave off. I haven't heard any questions yet, so please, I'm open to floor for questions.
Thank you, Gert. And I do encourage all of you to attend Telluride next week. They were kind enough to shift a week later so as not to intersect with ICONS. So feel free to raise your hands or put questions in the chat. I'll go ahead and start with a question. Thank you for your great presentation. That was amazing. So you mentioned early in the presentation about metrics and benchmarks for neuromorphic, and you talked a lot about different hardware platforms, everything from fully digital to memristive and different types of devices to even FPGA-based systems. So do you have any thoughts about some of the benchmarks and metrics that we ought to be using as a community to understand the performance of our neuromorphic systems?
Right. That's a very good point. And some of the discussions will also be taking place at the Telluride workshop too. For many years, right, the community has been doing simple problems. Everyone is doing NNIST, or now ImageNet, right? But with neuromorphic intelligence, we can really get at different levels of metrics. So human interfaces are important, and we should really get at human interfaces too, get at intelligence. Also, what is unique for neuromorphic systems is this event-based representations. There are already some event-driven, there's an MNIST, right, a neuromorphic MNIST that is basically an event-driven version of those digits and the characters. But so we should think of more so challenges, specific challenges that require event-driven representations, and they can take advantage of this bandwidth, this asynchronous representations that are very different from this frame-based representation that you typically have, that you have in vision. There is energy, there's performance, and you have to carefully quantify performance, right? So I think it's okay first to go after the traditional machine learning AI benchmarks. Of course, we're handicapped because there are some aspects of neuromorphic computing that are hard to meet with those very efficient cellular neural network or those cellular representations, those convolutional representations that we have. But there are also advantages that traditional machine learning systems don't have. So we have to both get after the metrics that AI is using, but then we can also then go for metrics that are unique in our approach for neuromorphic, such as resilience. Does a thing fall apart when you remove one transistor, right? So, and we should have examples where really we pull out the chip or we bombard it with radiation in outer space, in space, right? So we should have some benchmarks where we can also test if not only performance and efficiency, energy efficiency, but also resilience too, right? And this is a challenge. I'll leave it open to the community for figuring out what it will be.
Yeah, absolutely. And so I have another question while we're waiting for questions from the audience. So we've heard a lot about specifically neuromorphic and robotics in the last couple of days as a potential showcase for neuromorphic technologies. But I think another one, and you sort of touched on it at the end, is these sort of brain-machine interfaces. Can you talk a little bit more about the work you're doing with those?
Yes, so and this is in our group. So Fred Borkar has a nice review paper on the topic in the Journal of Neuroengineering on neuromorphic neural interfaces. So the community is so there has been great work at the University of Bordeaux for many years on this topic, right? Interfacing neuromorphic models, neuromorphic chips with actually neurons, even with intracellular recording of those neurons, right? And there means for actually teasing apart neural function, right, by directly coupling that neuromorphic systems and with neurons at this cellular scale, right? There's some nice work also by Giacomo Ineveri on the ECG and other kind of brain computer systems too. So yeah, it's very exciting. And it's just starting. But being in a bioengineering department, we're very sensitive about actually making impact, clinical impact. And so that has been underrepresented in the neuromorphic community. Right? There are definitely good applications. I mean, think of it, neuromorphic is about spikes, right? So you have these representations. It makes sense if you have new implants, right? So for, say, brain implants, for, say, alleviating stroke, it makes perfect sense to have this transducers of spiking input activity, spike sorting, all that stuff, and then eventually going out with activating with electrodes, right? This transduction should be event-based spikes, right? And so it makes perfect sense to have this neuromorphic approaches for doing that as well.
Yeah, absolutely. They speak the same language. So anybody have any questions? Feel free to raise your hand or just unmute or pop a question into the chat. I know Gert has an extremely busy schedule today, so I think you have a meeting right now, actually.
Yeah, unfortunately, I have this committee meeting. I can't get the last committee meeting of the year, file review. So yes, and they're waiting for me. Yes.
So we maybe have time for one more question if anybody has a question to ask. If not, I will thank you so much for your presentation. That was great, and thank you for participating over the course of the conference.